Okay, so the topic for today is going to be lower bounds for randomized algorithms. I mean, this is of course not just a topic, but sort of an entire subfield in of itself. But specifically what I want to tell you is one of the most classic techniques, which is known as Yahoo's Minimax lemma. And we will apply this to get lower bounds for regret minimization. So while many of you are maybe familiar with Yahoo's Minimax lemma, I think the lower bound for regret minimization that I'm going to show will be different. It might not be something that you see. So hopefully there's some new stuff here. Okay, so let's actually start. Let's go backwards. Let's start from regret minimization. So we saw the experts problem. And remember that, just to recall, regret was basically the loss of the algorithm minus the loss of the best expert. And so we had n experts, and we had t was the time horizon, so this is the number of time steps. And remember, all the losses were in each individual loss, that is for every time step. The loss function values were in 0, 1. And so we discussed two different algorithms for regret minimization. So we looked at randomized weighted majority. We also saw follow the perturbed leader. And these were two algorithms that behaved very differently. And these were both randomized algorithms. As we discussed, any deterministic algorithm will have linear regret. And what we showed for both of these algorithms was the expected regret. The expected regret, we showed was something like root t log n. So these two very different methods ended up giving the same regret bound, and it is natural to ask, can we beat this bound? Can we actually improve on the regret? So you have n experts, can we get something less than root t log n? And remarkably, the answer is no. We can prove a lower bound. We can prove a lower bound that for any randomized algorithm, there exists some sequence of loss functions such that the expected regret is actually at least root t log n. So this is a very satisfying resolution to the experts problem in this setting, of course. I mean, there are many other settings where there's a lot of other math and a lot of results that are still being found. But for this basic experts problem setting, we have two different algorithms that give root t log n regret. And what we can prove is actually that's optimal up to the constant factor. Meaning for any randomized algorithm, there is a sequence of loss functions so that the expected regret is omega root t log n. And the aim of today's lecture is going to prove this bound using a tool called Yahoo's Minimax Lemma. Okay, so essentially let's start now before digging directly into how to prove this bound. Let's try to argue about how does one prove lower bounds for randomized algorithms. So how to prove lower bounds for randomized algorithms. Now this seems quite challenging because unlike a deterministic algorithm where you sort of know exactly what its behavior is and therefore you can try to tailor a bad input for any deterministic algorithm, a randomized algorithm has random choice, so it seems a lot harder to sort of tailor a sequence of inputs, or in this case a sequence of loss functions, because you don't know exactly what the algorithm is going to do. So if you were to think of this from the perspective of, it's often useful to think of this as the perspective of a game. So you have the algorithm on one side and you have the input, and you can think of this as an adversary. So the algorithm wants to minimize, in this case it wants to minimize the regret, but you can also think of it in general as it may want to minimize something else. So let's think more abstractly, not just for regret, but you could try to minimize the regret, maybe minimize the running time. So often Yahoo's Minimax Lemma, or this context, is used to prove running time lower bounds or approximation, whatever. There could be anything. The algorithm is trying to minimize. The adversary is trying to maximize this quantity. So the adversary is kind of thinking on how to construct the right input sequence to let's say the loss function sequence to maximize the regret. And so we can think of this as a game. This is a game between these two players. We are the algorithm designer, and we are trying to fight against an adversary, which you can think of as nature, or you can think of as some source that is generating the inputs. Now, when the algorithm is now, so now let's flip our viewpoint. We're trying to prove lower bounds. So let's now, behave like an adversary. So you have an algorithm, and you're trying to construct an input that is going to maximize regret, except that the algorithm itself is randomized. And so this seems extremely challenging. And so what Yahoo gave was a beautifully simple tool that allows us to do this. Okay, so let me sort of tell you the high level idea in Yahoo's Minimax Lemma, and then we'll look into the proof of the formulation. So Yahoo's Minimax Lemma. Essentially what it says is we want to prove a lower bound, and one can think of it as abstractly as for some measure for a randomized algorithm. Okay, so, and here I'm going to say a worst case lower bound for a randomized algorithm. What Yahoo's Minimax Lemma says it suffices to prove a randomized lower bound for a deterministic algorithm. So you weaken the algorithm. You say now you only need to deal with deterministic algorithms, which is easier to argue. On the other hand, the inputs have to be randomized. So this was the input. And this is the algorithm player here, right? These two players, the algorithm, the input. So in the setting that we originally had, the algorithm was a randomized algorithm. The input was worst case. So you had a powerful algorithm and a powerful input. Yahoo's Minimax lemma says you can replace them both by less powerful players. So the algorithm is now going to be deterministic. So it's easier to hopefully argue about. The adversary who's generating the inputs has to be randomized. Whereas here they were worst case. So I'll explain this now in more detail. What's the key idea? The key idea, the key insight is really a randomized algorithm. A randomized algorithm is a distribution of deterministic algorithms. So this is, in some sense, going to allow us to look at this more formally in a game theoretic perspective. So I'm going to consider what I will call the cost matrix, okay, which I'll use bold C for. The cost matrix, where you can think of the cost, in this case, could be regret, it could be running time, whatever your quantity of interest is. The cost matrix of A and I is going to be the cost of a deterministic algorithm on the input I. So think of it as you choose a deterministic algorithm for regret minimization, and the adversary is going to choose some sequence of loss functions, and this is the regret of that algorithm on that sequence of loss functions. You could also think of it as running time. It could be the running time of a particular algorithm on some input. Okay? So I'm going to write this. Now, let us, for simplicity, just so that we don't have to get into to issues of like continuity and well-behavedness, let's think of everything as discrete. Let's think of everything as discrete and even finite. Right? So we could say that the number of algorithms is going to be finite. Like we could try to bound the representation size, maybe in bits. And let's just think of the inputs as finite. This is just going to make the discussion a lot easier, even though things carry out for the infinite setting as well. Okay, so here is your matrix. So I'm going to think of this as an algorithm. This is an input, and this is your cost. So this is the cost matrix. Okay, so does this make sense? Okay. So, what is the worst input for an algorithm A? So, whenever I use capital A and capital I, I'm talking about deterministic inputs. I will use script A and script I for distributions. So, what is the worst input over here? Or let's say, what is the worst cost instead of input? So you know that what you have is CAI, and you're just going to maximize over all inputs. Right? So this is just saying that so now think of this as a game. The algorithm player picked her algorithm. So the algorithm player plays the algorithm A, and the adversary will then find out the worst input play that input. And this is the cost. Right? So this is the game theoretic setting makes sense. We have two players here, the algorithm player and the input player. So this is like saying the algorithm player plays first, chooses an algorithm, then the input player plays second, and then at this point, this is going to be the worst case. Okay, now let's look at what is the worst case. What is the worst cost for a randomized algorithm, script A. Now, script A is a distribution on A. So it's a distribution on the rows, if you will. So now instead of cost, we have a notion of expected cost. So it's the worst expected cost, not the expected worst cost, right? It's the worst expected cost. So what is the expected cost? So I'll write this as an expectation over A, right? So A is being drawn from script A. Now we will look at the cost of A and I, and then we will maximize this over all inputs. Okay, does this make sense? Okay, so I just want to, just to make sure that you understand, I'm just going to state something, and I want you to make sure that you understand. Suppose I could also maximize over distributions of inputs. So let me say I want to maximize over all distributions of the expected cost of choosing the input from the distribution, then choosing the algorithm from its distribution of this quantity. Now clearly, that is true, because I'm maximizing over a larger set. Each individual input can also be thought of as a distribution. It's just the point distribution. But can you say anything more? Is this inequality truly an inequality? Any thoughts? For the input player, is it strictly better to choose a distribution on inputs versus choosing a single input?
Well, you could always just have your distribution be one of the inputs.
Which input?
No, I mean like the case where you only pick one input is a subcase.
Exactly.
In the case where you get to pick a distribution.
Correct. So therefore, that's exactly why this is why you have greater than equal to, or less than equal to. I'm sorry, right? Because when you pick a single input, that's a special case of picking a distribution. So this maximum is less than equal to this maximum here.
Oh, but you're asking about the opposite.
I'm asking about the opposite. Exactly. So it turns out these are actually equal. Now tell me why. So let's look at the expectation of A generated from the distribution CA star as a vector. Right? So this is going to be a vector. What is the vector? script A is a distribution on the rows. So I'm just going to take the average of the rows according to this distribution. Right? So this is going to be the vector of expected costs as a vector of expected costs. Right? So there are a bunch of costs here. Now think of it in terms of a game. The algorithm player has played first. So she has specified a distribution A that is being sampled from. So the algorithm player has specified her distribution. You, as the input player, need to choose either an input or a distribution on inputs that is going to maximize the cost. What will you choose? Suppose you knew what this vector is. What are you going to choose as either your input or your distribution?
Just the worst one.
The worst, which would be the largest coordinate. Right?
Yeah, always give the worst input.
Always give the largest coordinate. There is no benefit to playing a distribution. And that's because the input player plays second. Right? There's an asymmetry here. The algorithm player plays first because she needs to write down what the algorithm is. So she writes down the algorithm. She doesn't know what the input player is going to do, so she chooses a distribution to sort of hedge her choices. But once the algorithm player has committed, the input player will simply go and pick the worst case. Right? So if you look at this as a vector, the input player chooses the index of, which is really the input, this is the input, the index of the largest coordinate. Right? So the input player cannot get a cost strictly larger than this by picking a distribution. Right? Does this make sense? And therefore, these are actually equal. Therefore, these are equal. So, any questions about that? This isn't fundamental for the proof, but I think it is useful for you to see this so that you understand what's going on here. Okay, so these are actually equal. Okay, but having said this, actually this is going to be important for the proof. This is going to be useful. Let's go back to what we were looking at. So we were looking at this quantity, which is the expectation of A generated from script A of the cost of AI. Now, this is the worst case cost of randomized algorithm script A. So if you wanted to find the randomized algorithm with the smallest worst case cost, in some sense the optimal randomized algorithm, you would minimize overall distributions here. So this is equal to the lowest worst case cost of a randomized algorithm. This is the lowest worst case cost, right? So I'm first, so this is like saying that, so here's the game, right? The algorithm player plays first, then the input player plays. I should say, then input plays. So algorithm plays first, then the input player plays. So the algorithm player thinks, okay, if I chose this distribution, then the input player is going to maximize. Therefore, I will pick the minimizer of the maximum. Right? And so now let me give you a theorem here. It's a fairly simple theorem, but a profound one. It basically says, which is intuitively makes sense, right? That if algorithm plays second, the cost cannot increase. Obviously, because the algorithm player can now choose her algorithm according to the input rather than the other way around. And this is where this is also said that Minimax is greater than the Maximin. So now if I minimize over all algorithms, I maximize over I do the expectation over the algorithm being chosen. This is greater than equal to flipping the order of these, except I have to be a little careful. So now I'm going to maximize over all distributions of inputs, minimize over the algorithm, except now I'm just going to minimize over individual algorithms. And this is an expectation of I and I with the cost A I. Okay, so what's important to note here is two things. One is the flip. So the flip is in what we were originally looking at. Algorithm player plays first and plays a distribution. Algorithm is randomized, input is deterministic. Because input is just going to be the worst. And here, it's the opposite. The input player plays first, so plays a distribution. But then the algorithm player simply plays deterministically, which he can do. So essentially, the second player doesn't need to hedge because the first player has already fixed the distribution. So the second player will just choose the maximum coordinate in what I described earlier. So I guess what I described earlier is going to be a core part of what we are proving here. So any questions about what this statement
Sorry, you cut
means?
out for a second for me. Could you repeat that?
I'm just saying, well, I guess I said, do you have any questions? But probably before that. I'm just saying that there are two things that are important to notice here. One is the flipping of the max and the min, right? The max and the min are flipped. The second is the flipping of the distribution. Who's playing a distribution? The first player plays the distribution. So here it's a randomized algorithm, here it's a randomized input. The second player plays a point distribution, meaning that essentially plays deterministically. And as we argued before, it doesn't harm the second player to play deterministically because he or she can simply choose the worst coordinate. Okay, any questions?
I'm still a little confused for the previous equality that you showed. Could you just briefly go over that if possible?
For this one?
Yeah.
Okay, so think of it as, so the algorithm player has chosen her distribution, right? And you as the input player have to choose the input. and you're trying to maximize the cost. So what are you going to do? You're going to look at the algorithm has some probability of being this row, some probability of this row, so on and so forth. You will simply average all of those up as the weighted average. So you can look at the expected value of this vector, of the cost vector. Right? I put a star there because it's a vector. So you look at the expected cost vector. This vector, basically every coordinate says what is the expected cost if you as the input player chose that input. And it's expected because the algorithm is randomized. And so what is the input that you're going to choose? You will choose the largest coordinate.
Yeah.
Now, even if you were to choose a distribution of inputs, you're not going to beat the largest coordinate.
Yeah.
And that's what this is saying. That you
okay.
might as well just choose the worst coordinate. There is no benefit in choosing a distribution.
Okay, got it. So we're showing like the inequality in both directions.
We're showing the inequality in both directions, exactly.
Okay, that makes sense. Thank you.
Okay? I should note for people who have seen Yahoo's Minimax Theorem before and seen a proof, this is often said to be a consequence of von Neumann's Minimax Theorem. So actually, this is also an equality, but that's much harder to prove. It turns out that to prove the weak version, this is just weak duality. You don't even need the power of von Neumann's Minimax Theorem. You can just directly prove this, which is what I will show over here. So it's actually the easier side of von Neumann's theorem. But for the lower bound purposes, the weak version is enough. Okay, so let's prove this. And then once we prove this, we can then go and investigate what this is. Remember, we wanted to lower bound this quantity, and we have a lower bound given by this quantity here. And we will show that this quantity is about arguing. As you can see, it's arguing about deterministic algorithms and randomized inputs. Okay, so let's go backwards here. So let's start with the maximizer, the minimizer, the expectation of I over here of this cost. Okay. So remember, we said that, as we argued before, the second player gets no benefit by playing a distribution. So we can actually say this is equal to maximizing over inputs distributions, minimizing over algorithm distributions, and taking the expectations accordingly. Okay? So second player gets no benefit by playing a distribution. So now let's start from this expression here. So what we'll do is we'll pick I star, which is the distribution, to be the maximizer. Okay? And so now this quantity here can simply be written as the minimum over all distributions. The expectation of A generated from the algorithm, the expectation of I generated from I star, script I star, of the cost of A, comma I. Right? So I star is the minimizer. Now, I can just as well say this is at most, right? So I star was fixed. The input player played first. But using this, I can say, no, I can minimize over this, over A. I can now maximize over the input distributions and take the expectation of A generated from A, of I generated from the input distribution, cost AI. Okay, does this make sense? This is just saying that the input player plays second. The input player plays second. So this should be obvious. I mean, because the input player initially we said is playing I star. But if the algorithm player has already chosen her distribution, then the input player could potentially choose something better. He could choose I star, but he could also choose something better. And that would be the maximizer over here. Right? So does this make sense? Just look at it turn by turn. So ignore this, or ignore this and ignore this. Right? If this is confusing. This is just saying that for all A, the left-hand side, which is just looking at the cost for a specific I star, is going to be at most the cost of the worst I star, worst input distribution, which is the maximizer here. So this should be true for all script A. And then, of course, this will also be true for the minimizer. Okay, does this make sense? Any questions?
So this is like I star was chosen without the knowledge of A.
Exactly.
If we have the knowledge of A, then we can make something better, but we could always just choose I star.
You could always just choose I star, but you could potentially make it better. Exactly. Okay?
So is I star corresponding to a column of the cost?
Yeah, so I star is a distribution on columns.
Oh, I see. So
Right?
so it has a specific probability associated with each column.
Exactly, with each input. Yes.
Very cool.
Right? So, again, we're kind of flipping our viewpoint between who's choosing the distribution, and so it's either a distribution of rows and columns. And that is correlated with, of course, like who's playing first. So we're just saying that if the input player plays second, then he gets an advantage. And that's what this inequality is saying. Now, I'm just going to have that in front of you so that you can still see that expression. Okay, there we have it. So that expression is still there. Now remember, we said that this is going to be equal to the min over all A distributions, the max over single inputs of the expectation of the algorithm being generated from A, C, A, I. Right? And this is what we argued earlier, right? This is exactly what we said over here. The fact that this is an equality. So I can, obviously this is going to be true, this is true for any randomized algorithm, and this is going to be true for that optimizer as well. Right? And this is because a point distribution, or I should say point or singleton, singleton distribution is the optimal choice. And that's the end, right? That's the proof. So it's really simple. It's just like, but it's simple yet profound. You have to think about it carefully, what each of these statements means, and once you understand the meaning, the inequality is easy, the equality is also easy. And what that leads to is, of course, the Minimax theorem, right? This is exactly the expression that we wanted on the left-hand side, which I flipped the sides. But this is the quantity we want the lower bound, which is the worst cost of a randomized algorithm. Okay, so any questions about that? Okay. Now, max I, script I, min of capital A, the expectation of I generated from script I of the cost A. I, what is this saying? This is saying if we can find a hard distribution of inputs, or equivalently find lower bound for some distribution of inputs I star. So find a lower bound L for some distribution of inputs I star. Then, by the theorem, we know that the min of max, expectation of A generated from script A of this cost, we know that this is going to be at least L. And indeed, this is Yahoo's Minimax lemma. So Yahoo's Minimax lemma says, find a lower bound for some distribution of inputs. So construct some distribution of inputs that are hard, find a lower bound for that, and that lower bound is now going to hold for randomized algorithms. Maybe not for the same distribution. This is important, right? Maybe there's a different distribution, but it just sort of immediately gives you a lower bound. It's kind of magical when you think about it, because you end up with a lower bound for a much more stronger object, which is the randomized algorithm, which is the randomized algorithm. And you got that stronger lower bound because you proved a lower bound for deterministic algorithms, but you proved a randomized input lower bound. Right? So it suffices to find a hard distribution of inputs that works, that is, a hard distribution for all deterministic algorithms will give you the general lower bound for randomized algorithms. Any questions about that?
What do you mean by hard over here for all deterministic algorithms?
So hard would basically mean something that maximizes the cost. Something that has a large cost. So instead of hard, I should say high cost. And
does it have to be the highest?
It doesn't have to be the highest. It doesn't have to be the highest. Because the maximum is lower bounded by any individual.
Okay.
You don't need to find the worst. You just need to find something. Yahoo's Minimax lemma is an extremely powerful tool, even though it's very easy to prove, because it allows you to reorient yourself in trying to find distributions of inputs that are hard for deterministic algorithms. And this reorientation is extremely useful the vast majority of lower bounds that are proven for randomized algorithms, at least in TCS, all come by using Yahoo's Minimax lemma. I should mention, and I think I did mention, remarkably, this is an equality, meaning that it doesn't matter who plays first. And this is actually a consequence, or it's effectively like it's the restatement of von Neumann's Minimax theorem for a special case. A special case, of course, being, in this case, these are just linear functions. But the equality is von Neumann's Minimax theorem. I have often seen Yahoo's Minimax lemma being written, with the equality, although I feel that that is unnecessary, because to prove the equality requires extremely powerful tools, whereas to prove the inequality is quite simple. Okay, so any questions about that? If not, then we will move to regret minimization. Okay. So now let's go to proving regret bounds. So let us prove regret bounds for deterministic algorithms using randomized inputs. Okay, I want to make a comment here, which is, I think 2 lectures ago, when we actually talked about regret minimization, or we talked about the expert's problem, we proved the lower bound for deterministic algorithms. We said that the loss of the deterministic algorithm can in some cases be twice the loss of the best expert. Except in that case, the inputs were not randomized, they were adversarial. The inputs were chosen depending on what the algorithm is. Remember, like we sort of set up the loss function based on what the algorithm was going to do. Here, we can only use randomized inputs. So, right, the input player is playing first. So, the input cannot be tailored to the algorithm. And therefore, the lower bound is not going to be as strong as the lower bound that we had at that point. So it turns out that the distribution of loss functions is easy. The distribution of loss functions is really easy. Just random losses, or rather UAR losses in 0, 1. What this means is that for all time steps, loss function is an independent, unbiased coin flip. It's an independent, unbiased Bernoulli. Right? So in some sense, it's like the easiest loss function that you can think of. Intuitively, it's something where there's really nothing to learn. Right? Because everything is just uniform random. There's nothing to learn.
Oh, so it's like there's no way that you can find the best expert because everything is random, but because there's a lot of experts, one of them is likely to do okay.
Exactly. One of them is likely to do somewhat better than average, but this is going to require a careful calculation. But you got the idea. So what is the expected loss of, so for all algorithms A, the expected loss of A, what is the expected loss going to be? Right, it's a deterministic algorithm. What is the expected loss? So remember the capital T time steps. What is the expected loss? So imagine that, that when the algorithm makes the decision, then the next losses are decided. It's the same. It's statistically the same as the losses being predefined, but it just helps you think about things.
Square root t.
Sorry?
Square root t.
Why square root t?
Because the algorithm will, the best expert will incur a loss like t over 2.
No, but I'm just asking, what is the loss of an algorithm?
It's gonna be like t over 2, right? Like
Ex-
it can't learn anything.
So
So
the
it'll just be random.
Expected loss is t over 2, linearity of expectation. Right, because for any fixed algorithm, you fix the algorithm, at each point, it's going to choose some expert, but the loss of that expert is 0, 1 with it's 0 or 1 with probability half. So in expectation, remember, this is the expectation over what? This is the expectation over the LTs. Right, so I'm not going to write this out explicitly. I'm not going to write out what the expectation is over. But here I want to make this clear. The expectation is over the losses. So the expected loss is t over 2. So now let's look at what is, remember, the expected regret is equal to the expected loss of A minus the loss of the best expert by linearity of expectation. The expected regret is equal to the expected loss of A minus the expected loss of the best expert. Now we argue this is t over 2. The expected loss of the best expert. This is what we need to figure out. Okay, let me now introduce some notation. Let me say that xi is equal to the total loss of expert I. What we're looking at is what is the, and we need to upper bound this quantity so that we get a lower bound on the regret. What is the expectation of the min of x1, x2 up to xn? Right? And this is the expectation over x1 to xn. What is xi distributed as? What is the distribution of xi?
Binomial of t1 half.
Exactly, it's a binomial. That's the distribution. And now we need to figure out that if you chose n independent, so this is the minimum of n independent draws from the binomial. And this is what we need to figure out. We need to figure out what is the minimum of n independent draws. And by figuring out what that minimum is going to be, and technically how much the deviation of that minimum is from t over 2, we will get the regret bound. And this is the regret, and that regret will then translate into the lower bound for randomized algorithms over arbitrary inputs. Okay, so any questions about this? Now it's a little subtle here. We will prove So the lemma that I'm going to prove is going to say this is going to be at most t over 2 minus some theta root t log n. Okay, I'm going to prove this lemma. But when you plug this bound back in over here, you will get that the expected regret is omega root t log n. This is a non-trivial calculation, and I will show you how to do this. But then we'll get that the expected regret is now going to be omega of root t log n, and then from there we get the root t log n lower bound for regret. So before I launch into this calculation, let me pause, take a short break so that I can answer any questions that you have before we continue on the next part of actually proving this lemma here. This calculation here. Okay, so now we need to prove this lemma. So pictorially, let me sort of explain why this is going to be true. So what you have is the binomial t half, which is approximately. It's approximately, you can think of it as a normal whose approximately it's a normal whose mean is t over 2. Now what is the variance? Right? And so we know that the variance is just going to be t over 2 minus t over 4, right? Because the variance is going to be the sum of variances, and the variance of the Bernoulli is basically just half times 1 minus half times 1 minus half, which is going to be 1/4. So the variance is t over 4. Right? So this is just a normal distribution. So the standard deviation, the sigma, is going to be basically theta of root t. So what you have is you have a normal distribution, and most of the mass basically lies in something which is theta of square root t. This is where most of the mass lies. Okay, but where are we going to get this from? Now this requires some sort of careful thought here. So roughly speaking, the probability, okay, I'm going to do a rough back of the envelope calculation, and then we can do it more formally. The probability of deviating more than k times sigma. So the probability, now what is this deviation? What I mean is the probability that xi minus t over 2 is, or let's do the opposite, the probability that xi minus t over 2 is less than k sigma, right? Because we are trying to bound the minimum. So we're picking repeatedly from this distribution. We know that most of the mass is going to lie in here, but there are going to be a few outliers. A few things are going to go down there. The probability that it deviates more than k times sigma is roughly e to the minus k squared divided by 2. Now we're doing n draws. So if k is approximately root log n, if k was approximately root log n, then this quantity is going to be like n to the minus half. But if you do n draws, there's an event whose probability is n to the minus half. This is highly likely to happen for some I. It is highly likely to happen for some choice of I. So what this is saying is that x being less than t over 2 minus k sigma is highly likely for some I. And so this is essentially the argument. This is what we need to make formal. Any questions about the sort of intuitive? This is like a back of the envelope calculation, which is very important to be able to do before you sort of launch into trying to prove something. You do this somewhat quick and dirty calculation, and often the quick and dirty calculation, if you sort of do it correctly once you gain experience with it, will often lead you to the right answer. So does this make sense? Just saying that the probability of deviating by more than k standard deviations is e to the minus k squared divided by 2. It's actually not even important that there's a 2 there. So it's e to the minus k squared, which means if k is root log n, this probability for any individual expert, for any individual I, is going to be something like, it's going to be more than 1 over n. And because you did n draws, this is likely to happen, that there's going to be some expert who's going to be in that tail region. And that gives you the root t log n. Okay, so let me now do this a little more formally. So I'm going to write a simple claim over here. Let's say 2 to the minus t choose t over 2 minus s. Okay, so this is the probability of xi being equal to t over 2 minus s. Okay, this is just binomial coefficients. And so what you can argue is this is going to be at least, I'll write it down, alpha divided by root t e to the minus 4 s squared divided by t for some constant alpha. Okay, so this is an exercise, and this is basically, you just use Stirling's approximation. And I should say over here, no, I mean this is fine. So this is by Stirling's approximation. Okay, so what this is saying is your binomial coefficient is essentially 1 divided by root t e to the minus s squared divided by t, where s is the deviation. Okay, s is the deviation. So any questions about that? Right? So now the probability that xi lies in t over 2 minus, I'll say, root t log n divided by 8 to t over 2 minus root t log n divided by 4. So this is like looking at what is the probability of being in that tail region with roughly this deviation. Right, this I can just write as the sum of s going from t over 2 minus root t log n divided by 8 to t over 2 minus root t log n divided by 4, the probability that xi is equal to s. Using the approximation that we had earlier, I can just write this as s going from whatever its bounds are to alpha divided by root t e to the minus 4 s squared divided by t. So note that as s is larger, this quantity becomes smaller, so I can simply upper bound this by the sum of s going from whatever its bounds are, alpha divided by root t e to the minus, so let me just choose the largest value of s that is, I'm sorry, I should rewrite this differently. Sorry. My apologies. So I'm just going to write this as a sum of r going from root t log n over 8 to root t log n over 4. So I'm summing over the deviations, and this is the probability that xi is equal to t over 2 minus r. Okay? And now I can use my claim. I can say this is at most summation of r going from whatever bounds there are of alpha divided by root t e to the minus 4 r squared divided by t. So sorry, I flipped the choice between s and r, but this is what it really should be. And so now I can plug in the largest value of r. So I'll say this is at most r going from root t log n over 8, root t log n over 4. So that was the largest choice. E to the minus 4 divided by t times t log n divided by 16. Okay, so the root t log n was chosen exactly so that the t will cancel out. And this is going to be equal to alpha divided by root t times the number of choices that I had there, which is simply root t log n divided by 8, times, remember, this thing is just going to be e to the minus log n over 4. Right? This is going to be n to the minus 1/4 times n to the minus 1/4. And so the root t will disappear. And so what I get is just alpha divided by 8 root log n to the minus 1/4. So this is the probability. So I'll just go back and write it at the top. This is the probability of lying in this regime. Okay. This is the probability of lying in that regime. Now I can say, what is the probability that there exists an I such that xi minus t over 2 lies in the regime minus root t log n over 8 minus root t log n over 4. So what is the probability there exists something? So this, So remember, the probability of lying in this region is at least essentially n to the minus 1/4. So the probability, I can lower bound this by 1 minus alpha divided 8 log n divided by n to the 1/4 to the power n. And then, sort of using my favorite approximation, right, this is 1 minus e to the minus alpha over 8 root log n divided by n to the 1/4 times n. Right, and this is just going to be 1 minus little o of 1. Or I should say, actually, technically, I'm sorry. Now, I think, I'm sorry, so I think I fudged my what is n and what is t here. Or okay, so let me just make sure that I've not fudged things over here.
I think this is fine.
No, this is correct, right? This is all.
You have x1, x2, xn. So yeah.
I have x1, x2, xn, and so this is the probability that something lies in this regime. Right. Okay. So I'll just write this is the probability of e to the minus, and I'm being a little sloppy here, but I can just write it as that. So it's going to be exponentially small in this quantity here. So essentially what this is saying is that with high probability, the deviation, the minimum, so let's just go back and say what this means. This means that the probability that the min over I of x1 up to xn, the probability that this min is at most t over 2 minus root t log n divided by...
Well, you're a little bit too high.
I'm sorry.
Thanks.
4. So this probability is essentially, it's overwhelmingly large with respect to n. This is overwhelmingly large with respect to n. And so now you can ask, okay, so now what is the expected value of this quantity? So we know that with probability, so remember we wanted to prove an upper bound of this form. So you can say with probability 1 minus e to the this is t over 2 minus root t log n divided by 4, plus with the remaining probability, let me just say that I said, well, I don't know, I'm just going to say the min is going to be at most t. Or let me be a little bit more careful here. So let me write down a quick and dirty calculation. The exact one is going to require a little bit more work, which I don't think is going to be necessary for this exposition. So in the worst case, I can just say, well, this is going to be at most t. Now, the regret lower bound that I'm going to give is, I'll just say, assuming that n is at least log t squared, I can essentially bound this by t over 2 minus theta of root t log n. So I need to have sufficiently many experts, and then this bound will work, because essentially this quantity will now kill this term over here. I don't need, in general, one can prove a lower bound for all n, even n is equal to 2. But you need to require some more care with Stirling's approximation. So the way I've set things up, this bound only holds for sufficiently large n, but even in general, you can get such a bound to work because all you have to do is to deal with this, even when you have just 2 experts. Of course, the n is now going to be 2. You can prove that the min is going to be sort of t over 2 minus theta of root t. You just need to do the Stirling's approximation, you need somewhat more care. Like I've been somewhat sloppy and I just put some constant over there, but if you were to follow the constant a little carefully, do the calculations, you can prove this for any number of experts. And so this then will complete our proof, because what we say is the expected min is at most t over 2 minus theta of root t log n. This is assuming that n, you have sufficiently many experts, but as I said, you can prove this for all n. And so when we put all these pieces together, so what are all the pieces together? So we said that the expected min is at most t over 2 minus theta of root t log n. That now proves that the expected regret is omega t log n, the expected regret for this distribution, right? So you have this specific distribution of losses where you have uniform random loss and 0, 1. So for this distribution, for any algorithm, the regret is omega root t log n. Then we go ahead and apply Yahoo's minimax lemma. And by Yahoo's minimax lemma, what we get is that this L that we had here was essentially omega root t log n. So we just constructed some hard distribution. With that hard distribution, now what we get is that for any randomized algorithm, we actually have a lower bound, and that lower bound is again root t log n. And essentially this then completes the proof, shows us that the best regret that is possible is omega root t log n, for which we have multiple algorithms that achieve that bound. So I'll end here. I guess I have a few more minutes, but I don't want to. I was initially planning on doing another Yahoo's minimax proof, but I think won't happen in 5 minutes. So I'll end here, and I'll take any questions that you have.